shut that down. Go here. Done. Share. Where is it? Right here. My screen. Start the broadcast. And optimize for video. Start here. Let me log in here as well. Right there. Join. My personal. That one, not that one. No. This one. Done. Don't connect. Come on. All right. Stay as a participant. Looking good. All right, gentlemen. Are there any burning questions before we get the party started today? Any burning questions? View settings. Single page. Okay. So let me see. So today we're going to be continuing our exploration of chapter 2, which is basically an application of the derivative, right? So chapter 1 was focused on introducing the derivative and trying to get some of those techniques down. Again, when we first introduced it, the derivative is the slope of the tangent line at a point, all right? And then the first technique that we had for finding the derivative was the limit as h tends to 0 of the difference quotient. You know, a simple problem could take up like a whole page. And then, so after that, we explored some more sophisticated techniques for finding the derivative. And so that's where we did like the power rule, the sum and difference rule, product rule, quotient rule, chain rule, right? All of that kind of stuff. And then, you know, a little bit of applications of those. So then I think with chapter 2, we started looking at applying the derivative to like exponentials and logs, right? And I think, so last time we kind of reintroduced or revisited the exponential. And then the main takeaway with the derivative of the exponential function is that the exponential function is its own derivative, right? So when we go to take the derivative of e to the x, you know, it gets back itself with a few augmentations or caveats, right? So we're going to extend that notion to derivatives of the natural log function, right? So again, we've explored the derivative of exponential. Now, let me make sure. Did we do 2.1? Let me check real quick. I think we did. We should have, 2.2. Yeah, we did. Wait. Yeah, we talked about that. So let's keep going. Okay, and as always, if you have questions, feel free to either type it in the chat or the Q&A, or feel free to unmute yourself and we can talk about it and make sure it gets resolved. So just keep in mind that exam 1 is going to be rapidly approaching, right? So I think exam 1 is basically based on chapters 1 and 2. All right, so we finished chapter 1. We'll probably finish chapter 2 like next week. We got the next one of those two. So soon. All right. Today our goal is to go through 2.3 and 2.4. I think, well, next week, you know, so far we've been doing 2 sections a day. Next week the rhythm slows down. It reduces to approximately like one section per day. You know, give or take a few. All right. Okay. So let's go ahead and hop into section 2.3, derivatives of natural log functions. So a few objectives here. Differentiate functions involving natural logarithms and solve applied problems involving natural logarithm functions and their derivatives. Okay. So for any positive number x, the derivative of the natural log is going to be 1 over x. Right. So the derivative of the natural log is just 1 over x. Okay. So that's like one of the shortcuts like that we have from before. Okay, so in this example, we're asked to differentiate. Let me see. So we have y equals 5 natural log of x. So again, when we take the derivative of a constant times a function, essentially that constant can just go in front of the derivative. So this is just really 5 times the derivative of natural log, which we just said was 1 over x. So that means that the first result should just be 5 over x. Kind of. Okay, I'll just spare the details. Again, the derivative of natural log is 1 over x. So then dy by dx in this instance ends up being, it should be 5 over x. Hope everyone is doing well, you know, with all the chaos that's going on. Okay, so in part B, when we go to take the derivative, it looks like for that first one, we need to take a moment. Hopefully you can at least think of the name of the technique that we're going to use, right, for that first term. And hopefully, pardon? Hopefully you're thinking the product rule, right? Let's go participants. Okay, cool. We don't let that ride. Okay. So for the derivative of the first term, we have to apply the product rule. I'm just going to apply it without writing out the details. Let me see. So when we go to find dy by dx, the first is this guy. The derivative of natural log is this guy. So that's the first times the derivative of the second plus the second, which is this guy, times the derivative of the first, which is this guy. Okay, so that's first times the derivative of the second plus the second times the derivative of the first. That's the product rule. And then the derivative of 4x is just 4. So I'm going to put a plus 4 here. We can do at least some simplifications. This guy turns this into a 2. We could, I think that's about it, really. Okay. So then it looks like ultimately, I mean, they both have x squared. We could factor it out. It didn't really help us that much. Okay, I'll go ahead and factor it out. So if I factor out, and I don't know if that's making it any better or not. Let me just kind of glance and see if they factor or not, just for the sake of space. They did not, right? So we're just gonna take this. So we got this x squared plus 3x squared natural log of x plus 4. Okay. Now say you get on a quiz, well, not really a quiz. Keep in mind with all of our assignments, we get unlimited attempts. So if it's something, usually the quizzes have like 5 questions. If you get it wrong, you can take as many times as you like until you get whatever score you like. With the exams, you get unlimited attempts as those. Well, my voice just cracked, like I'm back in puberty or something. With exams, you still get unlimited attempts. It's just that you can't see your score until you submit the whole exam, right? So you can challenge questions on the exam. Like you can screenshot it and say, hey, I got this question right, but they marked it wrong. Could I recover some points here? And then I can look at it. And if you don't want to go through that kind of drawn out back and forth process, you're welcome to take the exams as many times as you like until you get whatever score you like. Again, unlimited attempts, the system is set to take your highest score. Okay. All right. So with part C, let me see, what's the time? Let me see. We got an hour and 15 minutes, so 40 minutes, so 6:40. Okay. Hey, Google, set an alarm for 6:40 p.m.
All right, your alarm's set for 6:40 p.m.
So that way I at least know that time-wise it's about the halfway mark, so I can be trying to move on to the next section. I'm trying to decide if I want to do the quotient rule or rewrite it rewrite this rational expression with the negative exponent, so I can just use the product rule. I think I'll just go ahead and do the quotient rule. So the quotient rule is low D high minus high D low over low low. So when we go to find, I know that sounds so silly, dy by dx, but that's just how I remember it. So low would be this guy. D high, so the derivative of that is going to be this. Let me see, low D high minus high D low. So the high would be this guy. D low would be this guy. All over low low, which would be this guy. Okay, then it's a matter of like combining like terms and simplifying. This turns this into a 1. We could factor out an x from both terms, right? If we do, those are going to merge. I got to keep in mind there's going to be a 1 there, and they're going to cancel to turn this into a 3. Okay, so let's see if we can catch all those changes. So then ultimately it looks like we have 1 minus 2 natural log of x over x to the power of 3. Okay, let's see, how do we do? Okay. 5 over x looks good. I think that was fine. X squared plus 3x squared natural log of x plus 4. 1 minus 2 natural log of x over x cubed. Okay. Okay, not too bad. All right, so we've introduced the derivative of the natural log. Again, the derivative of the natural log is just 1 over x. So then here, this is kind of like the whole extended power rule. It's like basically taking the derivative of the natural log and combining it with like the chain rule, right? So the derivative of natural log of some function is still going to be 1 over that function, or 1 over x essentially, but 1 over f of x times f prime, right? So it's kind of like we're doing the derivative of the outside function times the derivative of the inside function, similar to the chain rule. Okay. So the derivative of the natural log function, the natural logarithm of a function is derivative of the function divided by the function. That's fine. Du by u. That's fine. Okay. Or f prime over f. Okay. Okay. So we have a few examples here. I'll do a couple. Let me see. I'll at least do the first one. And I'll leave the others for exercise. So then our dy by dx, so 1 over u, so then, so the 3x, yeah, just the u, the f of x goes to the denominator times f prime. So the derivative of the inside function in this case is just going to be a 3. So then ultimately that's just 1 over x. Okay. I'll go ahead and do b. All right, so for b, again, dy by dx, f prime over f. So in this case, it's the bottom just persists, x squared minus 5. The derivative of the inside function looks like it's just 2x. And I think that's it there. Duplicate it. I don't think we can get anything to cancel. So we're just going to go with that. C, our dy by dx. So f prime over f. Okay. So our f is natural log of x. The derivative of natural log of x is 1 over x, which simplifies to 1 over x natural log of x. Again, I just did f prime over f. You can kind of do those individually and then just put them together and use your algebra to simplify. Duplicate. It like got hot all of a sudden. Like it's been moderate. But I don't know if it's just because I'm talking, thinking up, you know. I mean, I was gaming. I don't know. That's why I'm 9 times out of 10, if I'm almost late, either that or I'm just trying to get home. And I ended up having to cut my game short. I tried to do a quick match, usually a match that takes 10 minutes, and I had 15 minutes on the clock. And for whatever reason, it was just dragging out. I was like, you know what, guys, I gotta go. Like they kept attacking one by one. I was like, you know what, I'm out. So I'll probably have a penalty in my account, but I don't care. I don't care. Okay. It's so bad. I tried. I pushed. I kept pushing, but I don't know. They kept attacking one by one. And I was like, you know what? I gotta go. Okay, so let's go ahead and do this one. Oh, well, that should have been f prime for c. Let me go ahead and make that change. Right here. That should be f prime. Okay. So then f prime here. Okay, so the denominator, I guess you can flip it. So if the inside function was in the denominator, keep change flip. So when you have one fraction divided by another, so I'm just going to flip that fraction like this. And then f prime, oh man, darn it. Okay, I guess we got to do, we could distribute that x and then work that one. That might, but I think I'm going to just go ahead and do the quotient rule. It'll be okay. So the bottom times the derivative of the top, low d high minus high d low is a 1 all over low, which is this guy. Okay. Now we got some cancellations at play here. At least this x cancels one of those guys. Okay. Let's expand and simplify. Let's see. Okay, so that's gone. That's a 3x cubed. Looks like we got to distribute a negative. So then we get a negative x cubed minus 4 over, and let's I'm gonna leave it separated for now. It's like x times x cubed plus 4, just in case I can get something to cancel. Okay. It doesn't look like anything will though. Let's see. So 3 minus 1 is a 2x cubed minus 4 over. Yeah, I think I'm gonna just leave it. X times x cubed plus 4. Okay. We factor out a 2, that'll be x cubed minus 2. Yeah, nothing. I don't think I can get anything to cancel there. So I'm gonna let this be my final. Now, simplifying these sometimes gets a little, gets a little dicey. Let's see what happens here. Okay. 1 over x looks good. 2x over x squared minus 5. 1 over x natural log of x. 2, yeah, that's exactly what we got, right? 2x cubed minus 4 over x. Yeah. Yeah, we're good. Okay. I feel like there should be questions, but again, I acknowledge that, you probably just need some time. Now, hopefully you've already looked at this stuff in advance, because again, if you started using my recordings, the stuff I'm saying now should be like practically identical to what's in those recordings. So again, you don't have to wait for us to be live to go through this material. Again, the recommendation is to use my recordings to get ahead, and at least if you can get like a week ahead, that's a decent position to be in. Again, there's nothing stopping you from going ahead and finishing all the assignments for the semester. You don't have to wait on us. The only thing that you kind of have to wait on are the scheduled releases of the exams. Aside from that, there's nothing stopping you from using my recordings, taking notes as if you're in class, write down your questions. If you're like kind of really far ahead, then ask me those questions off to the side. But if you're asking questions relevant to like whatever section we're talking about for that day, then you can ask during class. Idealistically, because it's I don't think it's reasonable to like answer questions from chapter 3 and we're still on like 2.6 or whatever. You know what I mean? During class time. But again, that's the recommendation. Okay. So let's see. So example 3, in a psychological experiment, students were shown a set of nonsense syllables, such as the following and so on, and asked to recall them every minute thereafter. The percentage R of t who retained the syllables after t minutes was found to be given by the logarithmic learning model given as such, as t goes from 1 to 15. What is that, minutes? What percentage of the students, let me see, the percentage, okay. What percentage of the students retain the syllables after 1 minute? So I guess that's when t is 1. And then find R prime and 2 and explain what it represents. Okay. So the rate of change, like the derivative should be the rate of change, the percent they remember per minute, right? So after each minute, what percent do they remember? Anyway, so part A, what percentage of the students retain the syllables after 1 minute? Again, I'm assuming that means like when t is 1. So if we just plug 1 into this function, the natural log of 1 is 0, right? So that second term is gone. So it looks like it's 80%. That one should be 80%. I just plugged in a 1 for t. So it looks like 80% of the students should retain. I'm just going to mark that one as 80%. Okay. So then if we wanted to take the derivative, right, R prime, that first term is gone because the derivative of a constant is 0. And then the derivative of the second constant, again, the second term, that 27 goes in front. So we're really just doing the derivative of natural log of t, which should just be 1 over t. So then ultimately it's going to be what, a negative 27 over t. But then we want R prime of 2, right? So then R prime of 2, we said what, negative 27 over t? So there should be a negative 27 over 2. If that was a 13.5. So then negative 13.5% per minute. All right. So what we're saying is that after 2 minutes, the students are forgetting approximately 13.5% each minute at that moment in time, right? So that's the percentage that they're remembering or that they're retaining at that time. Let's see, how do we do here? Okay. So 80% and a negative 13.5. The result indicates that 2 minutes after the students have been shown the syllables, the percentage of them who remember the syllables is shrinking at a rate of 13.5% per minute. Okay, that's fine. I think what we said was a little bit different, but it was close enough. Okay. Oh man, we are like moving and grooving. We're already done with this section. Okay. So that was a derivative of the natural log of x, right? for all positive x. And then when we take the natural log of a function, it was f prime over f. Okay. I'll make a copy of this available at the end of class, and let's just go ahead and hop into the next section. So next, well, let's go ahead and do this one first before I talk about next week. Okay, so let's go to view, single page. That looks good. Okay. Okay. So here we're moving into section 2.4, applications uninhibited and limited growth models. A few objectives: find functions that satisfy dp by dt equals kp, and solve application problems using exponential growth and limited growth models. So function y equals f of x satisfies the equation dy by dx equals k times y, or f prime equals k times f of x, if and only if y equals c times e to the kx, or f equals c times e to the kx for some constant c. So I think what I want to say is the main takeaway here. We say that a function satisfies this equation if and only if that function is basically an exponential function of like exponential. I was going to say exponential growth, but it's essentially an exponential function, all right? And this is playing off of the property that the exponential function is its own derivative, right? So when you go to take this derivative, it's going to be some constant times itself. So again, this is really just a play on exponential functions, the property of exponential functions, okay? Okay, so let's see how we do here. So find the general form of the function. Okay, that's fine. Find the general form of the function that satisfies this equation. Basically a prime equals 5 times the original. And then on the previous slide, we just said that a function is going to satisfy, if a function satisfies this guy here, then it has to be basically an exponential function of this form at the bottom. So it has to take on the form a equals c times e to the power of 5t. Is that it? That's basically just a direct application of the formula. Yeah. Now, I kind of wanted to work it if we didn't have that formula. There's some algebra that we can do. Let me think about it. I mean, essentially what they did a direct application of the formula. Again, we have some derivative equals 5, or a constant times the original. That's only true if it's a exponential function. Right now, we could verify that this is the case, right? If we took the derivative of e would be itself times the derivative of the power. So it's going to be what you see there times 5, which is basically going to be 5a, right? The takeaway here is that this was a direct application of theorem 9. We'll get somewhere we'll be able to work backwards a little bit. But this is just a direct application of the previous. I'm going to let that one be for now. Okay. So this equation, or p prime equals k times p, is the basic model of uninhibited or unrestrained population growth, right? Whether the population is comprised of humans, bacteria in a culture, or dollars invested with interest compounded continuously. So then the population, so you can do p of t equals c e to the kt, or p of t equals p naught e to the kt. The first one is like population. The second one might be, it can still be population. Yeah, just two different ways that we write it. Where p naught is like the starting amount, same as c. C is the starting amount. Where c is the initial population p naught, and t is the time, okay? Trying to get to an example. So suppose that an amount p naught in dollars is invested into a savings account where the interest is compounded continuously at 7% per year. That is, the balance p grows at this rate, okay? Find the function that satisfies this equation and write it in terms of p naught and 0.7, okay? So before I go to the others, right? Again, I just can't shake, using theorem 9 that we just introduced. Let's see. So p of t, I guess I'll write it here for now. It should take on the form p naught times e to the kt, all right? Okay. That 0.7 should be our rate. P naught. Okay, we got p naught. Okay. So then for this example, the 0.07 is going to be our k. So then our future amount is going to be our initial amount times e to the 0.07 times t. That should be it. And I mean, essentially, I just use like theorem 9, you know. Also, or you can like use from college algebra that this is like exponential growth. Now, exponential growth, like in continuous compound interest, this is like PERT. I usually call it PERT. But once you get this, then you can like do the derivative just to check to make sure that the derivative is going to be 0.07 times the original, right? I'm just going to go with this for now for the sake of simplicity. Suppose that 10,000 is invested. What's the balance after 1 year? Okay, so we're starting with 10,000. We want the amount after 1 year. P naught is 10,000. E to the 0.07 times 1, right? So I think we have everything. We can just calculate. We just use a calculator at this point. Okay, let me pull up my calculator. Okay. Batteries holding on. So maybe we'll get to some of the homework today. We might have a little bit of extra time. It's fine here now. Right here. Okay. I need to do the grades. I guess I need to do grades for everybody. Okay. So let's just do 10,000, 100,000, 10,000 times E, 0.07. That's it, times 1, right? Because it's after 1 year. So 7%. 10% would be what, 1,000. 1% would be 100. So what, $700 added on? No, a little bit more because it's exponential. Yeah. Okay. So when we did this in the calculator, we got approximately 10,725 and 8 cents. Okay. So if 10,000 is invested, how fast is the balance growing after 1 year? So the rate of change. So if we want the rate of change of this guy, we just say this result times the 0.07, right? So we have the function, we have the scenario, we have like how much is going to be in the account after 1 year. So then if we want the rate of change from the theorem, kind of in the center of the screen says, well, the rate of change based on those conditions, all you do is say 0.07 times your result, right? So we're going to say the 0.07 times that answer. Is there a question? So it's growing at that moment in time. It's growing at $750.76 per year. 750, 76. Okay. Just do the best you can there. Ask questions, especially when you're going through the assignment. Let me check here. Make use of the Ask My Instructor, or hopefully mute. Oh yeah. Also, you might want to make sure that your Morehouse student name is showing. I just saw somebody that says Zoom user, so when I go to do attendance, if it says Zoom user, I'm not going to know who you are when I go to pull attendance. So if you could, like, I don't know, you should be able to change your name. But you want to just set your default so they're showing your student name, so that way when I go to take attendance, because if I have to guess, I can assure you I'm going to guess wrong, right? So make it easy for me so I can make sure to get you your credit. Make sure that your name has your student name shown. Glad we had the time. Okay, I feel good about this. I feel like it's a little bit ambiguous, but the key items are there. So this all looks good. All right, I think we got it all. Now, say I want you to see here for their C, right? They took the original function and then they went on and found the derivative, right? Which we kind of bypassed. I just used the theorem. But they found the derivative. They got the derivative to be 700 times e to the 0.07 times t. So then after 1 year, they got the same result that we did. All right. But essentially, that's just 0.07 times the original. So, whichever technique you resonate with, that floats your boat. There's more than one way to correct way. Go about this again. I just used the theorem directly. They found the derivative. Either one is acceptable. If you try one and it doesn't work, try the other. Okay. Let's see. Let's try this one. So it says the world population was approximately 6.04 billion at the beginning of 2000. It has been estimated the population is growing exponentially at a rate of 0.016 or 1.6% per year. So the rate of change is going to be 0.016 times the population, where T is the time in years after the year 2000, right? So this is saying that the population is growing at a rate of 1.6% per year, okay? Your question? That's okay. Okay. All right. So find a function that satisfies these equations, assuming that P naught is this and K is this. Let's go ahead and do that first, right? So again, from that theorem, in order, if a function satisfies dp by dt equals, I think it was K times P, all right? That if a function satisfies this, if and only if that function takes on the form P naught times e to the kt. That's it. All right, I think that's good, right? Because the whole takeaway is that when you look at the derivative, it's going to be that rate of change times the original. Okay, so then let's see. So we want to find our function. We're given the P naught, we're given the rate. I think that's everything that we need. Okay, so then for part A, that means that it should take on the form P of T would be 6.04 times E to the 0.016 times T. I just plugged in the P naught, I just plugged in the K. And so we know we're on the right track if, when we go to take the derivative of this guy, the result ends up being K times the original. All right? I'm just going to leave that as an exercise. But I feel good about this for part A. And again, that's just like the exponential growth model, like PERT, or when you're doing like continuous compound interest, it's all kind of the same thing. Okay. All right, so we're going to go with this. So then for part B, it says estimate the world population at the beginning of 2000. I think this is based on the year 2000. So what that means is that the year 2000 counts as year 0. Okay. So then if it's 2020, this is 20 years later. This is when T is 20. So then if we want to find P of 20, again, when T is 20, 6.04 E 0.016 times 20. So then at that point, it's a calculator problem. Okay. I feel like it's a little bit intense. I'm trying to be as clear as possible. Again, just do your best to try to absorb the takeaway points from here, and it really doesn't sink in until you go to do it on your own. Again, this is why I can't stress enough where it's a good idea to try to synthesize or process this information before class, because sometimes sometimes it's just intense, right? But if you had already seen this, yo, that pacing. Lay down, have a seat, lay down, thank you. Dog is like circling the room, making me anxious. I'm like, nope, just lay down, thank you. It's like distracting. It just makes like by the time I realized it, I was like, why do I feel so anxious? I was like, oh, because she's pacing. I'm feeling what she's feeling. Anyway, okay. She went. She's so interesting. Okay. So 6.04 times E to the power of 0.016 times 20. Okay. So we get this result. That's about right. That's what we anticipate. 8.32 billion approximately. Right. Population, they did what, 4 decimal places? 8.79, 3179. That's just the 4 decimal places duplicated. Billion people. Okay. I think that's reasonable for part B. Find the rate of change of the population at the beginning of 2020. So then from theorem 9, basically a repeat of the previous. Once we go to, if we want the rate of change based on these conditions, then we just take this answer and multiply it by our rate. So we're going to say that times, that answer times the 016. Okay. And the rate of change, you could say 13.3%. Let me see. So basically what I did, the rate of change of P of 20. We got approximately, and I'm gonna go ahead and write it as a percentage, 13.3086% per year. So what we're saying, duplicate, is that the population is growing by 13% per year at that after 20 years at that moment in time. That's the rate of growth of the population. Okay, let's see how do we do. Let's see how do we do. Okay, what's the time? We got plenty of time. Let me not get too overzealous. Let me see. I think we're good on the first one. That looks good. After 20 years, 3179 is good. 13. The rate of growth, million people per year. Okay, so I changed the units improperly. 133 is good. Let me think. People per year. Okay. So I don't know where I got percent. Those are off right here. Get rid of that. Move this. That was 0.13 billion. So then 33, I think it's million of people. Million people per year. Okay. Yeah, I think I was still stuck on the previous one. That's why I went to percent. Anywho, got my units a little off, but the rest of it was fine. All right. You okay? Okay. All right. Let's see. Let me give myself a little bit of power. I don't know about you all, but this is like my Friday. So when I'm done with you all today, then our weekend starts. So I tend to shut down, but it's all good mentally. All right. So we essentially got that one. Okay, so here we have our models of limited growth. The logistic equation given is one model for population growth in which there are factors preventing the population from exceeding some limiting value L, perhaps a limitation of food, living space, or other natural resource. So this is the limited growth model, right, where we're going to be exploring like populations, and initially they're going to grow exponentially, but then based on some limiting factor, they start off exponentially, but then they kind of finish. It's not really logistically. They just kind of finish. They kind of taper off, based on some limiting factor, right? The shape of it tends to make like an S shape, right? Okay. All right. Let's see. And this is generally how it looks, right? So this is the limited growth model. Again, it starts off growing exponentially, but then based on some limiting factors, it tapers off based on the limiting factor. Hey, Google, stop.
All right, I'm stop hitting alarms and timers that are ringing on your smart home devices.
All right. All right. So spread by skin-to-skin contact or via shared towels or clothing. Methicillin. I don't know. Resistant Staphylococcus. That's about the best I'm gonna do there. Auroras, MRSA, can easily spread a staph infection throughout a university. Left unchecked, the number of cases of MRSA on a university campus 2 weeks after the first case occur can be modeled by this. Okay. Yo, lay down. Lay down right here. Just stop pacing. Have a seat. You don't have to go to bed. Just sit down. Okay, so this is a model for the number of cases of MRSA on a university campus 2 weeks after the first case. Okay. So find the number of infected students after 3 weeks, 40 weeks, and 80 weeks. It sounds like just plug in 3, 40, and 80. Find the rate at which the disease is spreading after 20 weeks. So that sounds like we need to take the derivative and explain why an uninhibited growth model is inappropriate, but a logistic equation is appropriate for this situation. Then use a calculator to graph the equation. Oh, the uninhibited. Okay, yeah. Okay, that's fine. 3, 40, and 80. So we kind of need a copy of this. What I'm going to do, I'm going to go to my y equals. All right, so I'm going to clear all this out. Go to my y equals, let me see, in the numerator, I'll do parentheses, 568.803. Okay. I'm going to say divided by the denominator, 1 plus 62.200. Probably don't need those trailing zeros, but that's okay. E times e to the power of this negative 0.092 times x. So I'm letting x stand for my t. I want to close off the exponential and then close off the denominator. So basically put this as a function in my calculator, and then that way we can evaluate at those different times. Okay. So 3, 40, and 80. Okay. So I'm going to call on this function. On the right-hand side of the calculator, there's a button that says clear. Just left of that is a button that says VARS. I'm going to click on that button. I'm going to go to the right to go to Y variables. Number 1 for function, and number 1 again to call on the function we just typed in. I want to evaluate this when x is 3. Okay, so the number of cases after 3 weeks is approximately expected to be about 11 or almost 12. So let me see, the number of cases after 3 weeks, we got 11 point, we can do 8 on 1. Okay, then the number of cases after, I think it was 40 weeks, and then 80 weeks. Okay, so we did at 3. I'm just going to recall. I want to evaluate this when x is 40, 221, 422 cases. I'll get that in just a moment. And then I want to evaluate this when x is 80. Okay, 547, 151 cases. Okay. All right, it looks good. We're going to go with these. I'm just going to highlight them like this. Find the rate at which the disease is spreading after 20 weeks. So we need to take the derivative. Let's see. Okay, I might need some space. Let me see. Let me see if I can do the derivative here. I'll do it in purple. So then n prime of t, the bottom, 1 plus 62, 200, e negative 0.092t. The bottom times the derivative of the top, so all of that's gone, right? Because it's going to be a 0, so I'm going to just put times 0. So the bottom, low d high, the bottom times the derivative of the top minus the top times the derivative of the bottom. Okay, so that derivative is going to be itself 62.2 e negative 0.092t times the derivative of the power, which is going to be this negative 0.092. Okay, so the numerator is a double negative, which is positive. I'm going to go ahead and try to highlight it. Again, this is all gone because of that second term goes to 0. Okay, and then over the bottom squared. So then ultimately, it looks like n prime. Let me keep it in purple so it pops a little bit. So the bottom squared, let me see. We should probably multiply those numbers for the numerator. And I probably should give myself space, but you know, I'm just being whatever. Okay. 568.803 times this 0.092, 0.092. Okay, I think we can also do times that 62. 62.2. Okay. So it looks like we're getting this 3254. Let me write out the long decimal. 918287 times e to the negative 0.092t all over the bottom squared. I'm just going to write it as 1 plus 62.20 out of space. E to the negative 0.092t. I'm just going to put a squared there instead of, I'm not going to fold that out. I know that's hard to see. Let me give myself a little bit of space at least. I'm going to move this over. And then let me just rewrite this. So basically I'm just doing the denominator squared there. 1.62200 e to the negative 92t, quantity squared. Okay. So our claim is that that's a derivative. Let's go back to the question. Find the rate at which the disease is spreading after 20 weeks. So then we need to plug a 20 into this guy. So, okay, a couple of things that we can do here. We already have the original, I think, in our y equals. And I think this calculator can actually evaluate derivatives. It can't like give me the derivative, but it can, like, if I'm evaluating the derivative at like some value of x, then it can spit it out. Let me see. Oh, I got to think about it. I did it just the other day. Is it here? Okay, nth derivative. Let's try 8. Let's call on our function. We want to do this. We want to take the derivative of this function with respect to x when x is 20. Hopefully that works. Okay. All right. So after 20 weeks, our claim, the rate of change, we got this 4.3682 cases per week. And then what we can do, we can try our formula and see if we get the same result. Right, so that was us just using the calculator. It seemed like it worked. Basically, this function, we're saying we want to take the derivative of this original function with respect to x when x is 20, right? And this is the result we got. So then let's try ours and see if we get the same thing. I'm just trying to think how I want to type it. I'll go to my y equals and I'll put it in the second slot. I'll put it here as a function, okay? So let's see, 3254.91, nope, 91, 8287, okay, times e to the power of a negative 0.092 x, okay? That closes off the exponential. That should close off the numerator. We're going to say divided by the denominator, which is this 1 plus 62.2 times e is negative 0.092 x, okay? Close off the exponent, close off the denominator, and we want to say that that thing squared. That should be okay. Hopefully we typed it in properly. So then I want to call on that function, evaluate it when x is 20, and hopefully we get the same answer. God is good. It's close enough, right? Those trailing at the end like that is a little different because of rounding. That's why I wrote out the decimal, the long decimal, to try to minimize those errors. But it's a really good omen that we essentially got the same thing, right? So we can have some level, some sense of confidence in our result. And then for part C, explain why an uninhibited growth model is inappropriate, but a logistic equation is appropriate for this situation. And then use a calculator to graph it. Okay, so if we wanted to graph this, I'm going to suppress the second one. Hit enter. And then all we need is a proper window. We're going over 80 weeks, and we're going up to like 600 cases. Okay. So my window, my x values, we can go from -10. Let's go from like -10 to 100. Oops. Let's try this again. -10. That's fine. So like 100. This goes a little bit past. It's like So we can see just slightly left of the y-axis, and then we're going up to like 100 weeks, even though we collected data up to 80 weeks. On the x-axis, let's go in steps of, let's go by fives. Because if we go by tens, there will be 10 tick marks. I'm going to go by five, so that'll be 20 tick marks. The y-axis, the number of outcomes go up to about 600 cases. So I'm going to go from like 0 to 600. Or we can go from -10 up to 600. If we went by 10, I think that would be what? That would be like 60 tick marks. If we went by 20, that would be 30. What if we went by 30 per tick mark? 20 tick marks? 60? Let's go 30 cases per tick mark. Okay. So we should be able to see the curve. And it should level off. Right. Let me see, from my equation, where can we find that? So the L right there, KT. Oh, L is at the top. Okay. So it looks like the L should be 568,803. So if we did another equation where we said y equals 568,803, then we can kind of see that line, right? So if I go to my y equals right here, I'm going to do another one. 568,803. 803. Just so we can see that the line, and that's the line that's the limiting growth line. Okay. Factor. Okay. And so for this case, an uninhibited growth model is not realistic because, you have like, I think the main limiting factor would be what the number of students. It's not you don't have an infinite number of students. You're limited to how many number of students you have at the school. That would determine the number of cases, right, that you could have. So something like that. Okay, let's see, how do we do? 11.8, 221.6. Okay, it's a little bit off. Approximately 222 students is fine. 547.2 is fine. Okay, that's okay. The rate at which the disease is spreading after 20 weeks, 4.368. So, yeah, 368. Yep, cases per week. So after 20 weeks, the disease is spreading through the campus at a rate of about four new cases per week. That sounds accurate. And then unrestricted growth is inappropriate for modeling this situation because as more students become infected, fewer are left to be newly infected. So again, I think we said it was limited by the number of students, right? So the most you can have is like all the students are affected. So then it would stop spreading at that point. The logistic equation displays the rapid spread of the disease initially, as well as the slower growth in later weeks when there are fewer students left to be newly infected. So this is interesting that we're this little model or whatever. So just do the best you can. But it's a little bit of a story time. So like when I was in grad school, I want to say when I was in Florida, they used to have like games. It was like zombie games where you might start off with like one person infected. And like the people that were zombies, they would wear like an orange bandana somewhere on their body. And then it was like basically like a campus-wide game of tag. But then people also had like Nerf guns and like, so if a zombie got hit with a Nerf gun, then they it's basically like like airsoft. So if you get hit, then you can't turn somebody for like some amount of time, right? So, starting with one person, how many people can they turn? I guess everybody would have like an orange bandana on the person. And then whenever they get turned into a zombie, they would put it. So just a fun way of like a campus-wide game of tag. It was like tag with airsoft. Just, I don't even know what the point was. I don't even know if I played it. I just thought it was an interesting idea. It looked like fun to play. But yeah, that was something that we did in grad school at Florida Tech. And it's so trippy, like, oh man, they keep, I don't know if you've ever heard of like predictive programming, but they'll put stuff in like movies and things before it releases, and then just creepy stuff. I can kind of go into some weird stuff, but I'm gonna let it be. I think that was it for this one, and we still got a solid 20 minutes. Let me see. Yeah, we did the graph. I think we got essentially similar results. Okay. Okay, well that one was fun. Okay, so that was what, 2-4. Let's take at least 10 or 15 minutes to go through as much of the corresponding homework as we can. Just trying to think how I want to do this. I'll just add it on to the end of this. So here I want to add a page. And we're going to change the view to seamless. And it's going to give me a little bit of a hard time. This one, let me pull up my. Let me go show. Sign in. Let's go. Let's go. Allow this one here. Okay. And yeah, I want to take like at least 10 minutes. Allow. It's fine. Come on. Yeah, so my tablet, the device that I work on, they're basically trying to slow the device down. So their marketing, their programming, they won't allow me to like update my terms and conditions. So I can't log into my iCloud where it would have all my passwords. So I had to pull it from another device, and I know this is just a start. And every time they do an update, this is going to become more and more like they're intentionally breaking it. There's nothing wrong with the device. The device works fine. It's great. It does everything I needed to do. But and you know that Apple has been sued for this type of behavior before. So I know that they're going to get sued again, but they don't care because they got so much money. And I was like, as long as they give me some money, like not some money, but like good money, that you can brick it all you want. Just keep giving me money, and it'll be okay. Like just give me enough. And I was like, cool. But it's not okay. It's really wrong. But anyway, okay. But I know that they can be sued for this because they've been sued before. It set a precedent, and they don't care because they have so much money. All right, I'm just going to put this over here. So we just did, let me see. Now I can take requests up to 2-4. We got 10 minutes. Maybe we can try this quiz for this week. Yeah, let's just try this quiz. We got 10 minutes. Yeah, continue, hopefully it lets us take it. Okay. Late submission, 5%. Okay. All right. Let's see what we can do. Minimize this. Initial investment, P, annual interest rate R, and the time T are given. Find the future value of investment interest is compounded annually, monthly, daily, continuously, and then find the doubling time. Okay. Future value. So compound interest. So it's like P times 1 plus R over N to the power of NT, right? So we can actually do this in our calculator. I'm going to clear everything out, like clear this out and clear this out. I want all of this gone. Okay. So now for compound interest, the future amount, okay, let me see, a principal, which is the 3,500, 1 plus the rate. So that 2.25% we have to do as a decimal, so that's going to be 0.025. P times 1 plus R over N, number of compounding. So that's going to be our X, because that's the thing that's variable. There's changing to the power of N, which is our X again, times T, which is 5 years. So times 5, we just put it as 5X. Okay. So for the compound interest, again, the formula, P times 1 plus R over N to the power of NT. So that's the 3,500 times 1 plus R, 0.025 over N to the power of N times T. That looks good. So the only thing that's changing is the number of compoundings per year. Okay. So then I'm going to call on this function. So now it says for A, if it's compounded annually, that means we have 1 compounding per year. So we're going to let N or let our X be 1. rounded to the nearest cent. So 93 cents. So 39.59.93. 39.59. Let me see. 39.59.93. Let me hit enter here. Oh, okay. And then monthly, so that means our N is 12. I'm going to recall this, and I want to evaluate when X is 12. 30, 39, 65, 50, 39, 65, 50, 39, 65, 50. Okay. Daily would be what, 365? So change the 12 to 365 times in a year. 39.66. 39.66. I'm just going to go with that result. You good? Okay. Trying to at least get this one question. I'm watching the clock, so. All right. And then the future value when it's compounded continuously. So then for continuous compounding, we have to use PERT, which is a different formula. I'll do it here. Okay. So our principal, 3,500 times E to the KT. So that's the 0.025 times 5. Okay. Oh. Well, that's not a function there. It'd be nice if I could just copy that. Let me see if this at least spit out the answer. We might have to type it again. That looks accurate. Yeah, that's decent. Yeah. 39.6602. So 39.6602. Just for continuous, I use PERT there. The doubling time. So find the doubling time for the given interest rate. Let me see. Doubling time, natural log of 2. It's something like, there's a shortcut. I'm going to try to use a shortcut here. Okay, so I think our doubling time should be the natural log of 2 over K. It's basically like the half-life formula, but you have to use it for doubling. I think it's the natural log of 2 over K. And we have the K. I'm going to try that. Because I think that's a shortcut. Natural log of 2 over the rate, 0.025. How many years? About almost 30 years, almost 28 years. 2 decimal places, 2773. Because it's a quiz we can't see until we submit the whole thing. So I'm just going to go with it for the interest of time. There's more that we could do there. 5 years. So it's going to take 30 years for it to double. Yeah, that's a long time. Okay. All right, I'm going to just kind of go with that just for the interest of time. I'm going to let it be. So given that the natural log of 3 is this, natural log of 5 is this, find the natural log of 15. It says don't use a calculator. I'm just going to use a calculator. So natural log of 15 would be what? The natural log of 3 times 5. But the product rule says what the natural log of a product, the log of the product is the same as the sum of the logs. So we basically just add these two together. We don't need the calculator. So we're just adding these two results together. So it's a 2.71. 2.71. I'm going to go with it. That's a 172. Okay, we're going to go with it. What's the time? We got a solid 5 minutes. We're going to do what we can in 5 minutes. Okay, take the derivative here, right? So all the things we kind of been talking about. Let me switch this out. Off. All right, so that first term, so the derivative of x to the 6 should be 6x to the power of 5. Okay. The derivative of e is itself, so I'm going to say minus 7e to the power of 5x. But then we got to say times the derivative of the power, which is times 5. So that's going to turn this into a 35. I think that's it. Yeah, I don't see anything else. So I'm going to let that be. Maybe we at least got halfway through it. Okay, chain rule here. Okay. So the derivative of the outside function, the 1/2 comes out. I'm just kind of take my notes here. So we're going to have this 1/2. That's going to be to the power of a negative 1/2. Okay. And inside persists, so that's going to be a e to the power of x plus 6. So that's the derivative of the outside function. Then we got to say times the derivative of the inside function is going to be itself, is going to be e to the x plus 0, which is just e to the x. Okay. So let's kind of put this in the proper form. Let me see. Our numerator looks like it's just e to the x. Okay. The denominator looks like it's 2 times the square root of e to the x plus 6. Okay, I think that looks right? We kept our e to the x. That stuff is there. The 2 is there. Okay, I'm going to go with this. I'm going to get rid of my notes. All right, I'm going to just go with that. Let's try to get this last one. Okay, it looks like we're going to use the product rule. So first times the derivative of second, blah, 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 blah. Product rule. So the first is this guy. The derivative of the second is f prime over f. So 7 over 7x, which reduces down to 1 over x. So this becomes to the power of 3. All right. Again, it's going to be 7 over 7x. The 7's cancel. So then we're going to have x to the 4 over x, which becomes x to the cube. So that's first times the derivative of the second plus the second times the derivative of the first. Let me put the first in front to minimize confusion. So 4x cubed. Because if I put that 4x cubed behind, the computer might think that 4x cubed is inside the log, which is what I don't want it to think. So instead of putting it on the back side, I just moved it to the front. We could factor out the 4x cubed, but nothing really changes. So I'm going to go with that. All right. We got more? How many more? Oh, we got a good amount more. Okay. Thought I was done. Let me see. Let me just try to, I can do this one. Du over u. So the numerator, what is that? A 4x minus 9. And then just 2x squared minus 9x plus 1. Does that factor? No, I don't think so. I'm going to assume that it doesn't. It might factor. We might miss that one. I'm kind of short on time. The general form of this function. Okay. So it generally takes on the form c times e to the power of kt. Okay. So let's plug in the different parts. The 3 is our rate. Find the general form of the function. We could let c be 1. So I'm going to go with e to the power of 3t. All right. I'm just going to go with that. I just let c be 1. I didn't try to solve for it. I just let c be 1 there. Let me see. I think we got one more. The size of certain insect populations given by this for t measured in days. At what time of the population equals 600? So we're solving for t. Okay. So if we let the population be 600 divided by 200 gives us what? 3. So take the natural log. Okay. So then it should be the natural log of 3 divided by 0.03. Let's see if that works. So this is like our Hail Mary. What do we say? The natural log of 3 divided by 0.03. Again, I'm just trying to do a speed run, trying to get you guys out of here. Around the 1 decimal place, so 36.6 days. We're gonna go with it. 36.6 days. Okay. All right. Moment of truth. Let's see how do we do. Submit the quiz. We messed up. Okay, let's see. Let's see where we made our errors. I just want to see real quick. Probably that last one. Oh, we got a lot of these wrong. 3911. Future value. Okay, you know what? I probably typed something in the calculator wrong. And it's gone now. It is gone. Darn, I can't pull it back. So that means that we typed something in the calculator wrong. That's all that means there. 3959, yeah. Because once you have your formula wrong, then you can't get it right. But that's fine. We weren't that far off. Yeah, we definitely typed something in the calculator wrong. Okay, and let's see what happened here. See, I let C be 1. Okay, so that's fine. So that's fine. So yeah, we should have just put C, but that's okay. All right. Okay, well, that was pretty good for a speed run. All right. So then, like, if I were a student, now that I've seen those errors, we know we did wrong, we just take it again, and then we get our full credit. Are there any burning questions before we go our separate ways? That was a fun little thing. Okay. Let me see, just as far as announcements. So we just finished, 2.3 and 2.4. So I want to say next week we'll work on sections 2.5 and 2.6. I think the week after that, there might be a 2.7 and 2.8, and then we'll be ready for exam 1. Okay. Do what you can on your own. Be sure to make use of like the Ask My Instructor, things of that nature. It's okay, collaborate. Hopefully you got a study buddy, somebody in the class to work with, or make use of the tutors. And then if all else fails, then start making use of the Ask My Instructor. Okay. If there aren't any burning questions, we're going to go ahead and end the session here. And I will meet back on Monday, same time, same place. And take care.
Is it possible you could check my chat, Professor?
Okay, let me check out.
As we get
How you doing, Professor? I put in the chat. I don't know if you got it. My Zoom says Zoom user right now, but I put Nicholas on Gomez as Zoom user for attendance.
Can you change?
we're talking tickets.
Yeah. I have it on my computer. It says my regular name on it when I log in on my phone device because I'm at work right now, so that's just what it says.
Forecast. We're tracking a few scattered showers moving through our area this evening. Now tomorrow, the rain chance.
I mean, I'll get it this time, but I'm just saying, just going forward, if you just try to get into those settings, it's going to be much simpler if you just change it to your name than,
Stays.
I got you. Thank you again.
Let me see.
5 still just 20%.
Basketball. Do you know the days, Mr. Taylor?
I sent them to your email as excuses. If you could just check that.
Okay. All right. I'll try to, when I go to do attendance in a few minutes, I'll try to make that adjustment. If you don't see the change by tomorrow, just
But is it a better way to contact you? Because you haven't really got to go, so.
would you say?
Is it a better way to contact you?
My
You haven't really got back to the emails?
No, my office cell phone number. You can call
Okay.
it. Yeah. The emails
Right.
are call or text.
Okay.
Yeah. All right. Any other questions, gentlemen? Going once, going twice? And with that, we're going to end the session here. From one beautiful mind to another, have a great weekend, and we'll meet back on Monday, same time, same place. All right. Take care.